Hi everyone. So it's my pleasure to speak at this nearly carbon-neutral geometric topological conference. And today I'm going to talk about instantons and the depth of Taut foliations. So in the first part, I will introduce some basic concept for the talk. Okay, so the first thing, the main geometric topological object we're dealing with is called the balanced suture manifold. So roughly speaking, it's a three manifold with boundary and with some special a set of closed-oriented curves on the boundary called the suture. So, and this is due to Gabay, that a suture manifold M and gamma is a pair where M is a closed oriented three manifold with boundary, and gamma is a set of closed oriented curve on the boundary of M. So it's 0 in the first homology. Right, so this is slightly different from the original definition from Gabay, but as we will see, we'll only focus on balanced suture manifold, so this is enough for our purpose. So, and we have some object. Right, so A gamma, this is an annular neighborhood of gamma on the boundary of M. Right, so gamma is a set of curves. Right, and then A of gamma is just its annular neighborhood, and so R of gamma is the rest of the boundary, and we write R plus of gamma to be part of R gamma, so that the orientation from M coincide with the orientation from gamma. Right, so gamma will divide the boundary into two parts, and for each component of the complement of A gamma, so we can compare these two orientation. One is from the suture, this gamma, and one is from the original three manifold. Right, so three manifold is also oriented, and R minus of gamma is the rest. Right, and so, a suture manifold M and gamma is called balanced if alright, so there are a few conditions. Well, the first condition is that M has no closed component, and also R of gamma has no closed component. And the third one is that, we require that the Euler characteristic of R plus is the same as the Euler characteristic of R minus. So the condition of being balanced, right, is mainly on the third condition, right? But the first and the second condition are also important. Okay, so there are many examples about balanced suture manifold, so let me draw two of them. So we can have a three ball And we have one simple closed curve on the boundary. So this could be the suture. And say this is R plus and that is R minus, right? So the normal of the boundary is pointing outward. So we can also have a solid torus, right? But in order for the suture to divide the boundary into two parts, we need to have at least two of them, and the orientation is also very important. So if we give their orientation like this, then R plus and R minus as okay. So this is B3, the 3 ball, and this is S1 cross D2, or also known as the solid torus. And so these are two examples of balanced suture manifold. Okay, so right, and there's another very important definition. So a balanced suture manifold is called Taut if we have three more conditions. Well, the first is that M is irreducible. The second is that, well, R plus minus of gamma are both incompressible. And third, well, right, so R plus or minus of gamma are both norm minimizing. All right, so let me explain what are these three conditions be. So the first one, well, M is called irreducible if any embedded two-sphere inside M bounds a 3-ball. So that's called irreducible. And right, S inside, well, let's just say R plus, well, let's just say a surface. S inside M is called compressible. Right, so in the assumption we require incompressible. So compressible is the inverse, the converse to incompressible. So it's called compressible, well, if there's a curve beta on S. Well, of course, when I say, well, surface or a curve, we assume that they are embedded. And so that, well, beta does not bounce a disk on S, but bounce a disk in M. Right. So if we can find such a beta, then the surface is called compressible, and incompressible if such beta does not exist. Okay, so a third one, well, about the norm minimizing, well, for connected surface, as we can define a norm called x of s. This is the maximum of minus the Euler characteristic and 0. And so this definition is from Instanton. Right, so if a surface is disconnected, then the norm is just the sum of the connected component. So a surface is called norm minimizing if it realizes the certain norm among its homology class. Right, so the surface represents the second homology class, And well, there could be many different surfaces representing the same homology class, and the surface is called norm minimizing if it realizes the minimal certain norm among its homology class. Okay, right. So these are three conditions for suture manifold to be taut, and tautness. Well, the tautness is a key concept in the suture manifold theory. Okay. All right. So yeah, there is another very important concept. It's called the suture manifold decomposition. Okay, so a suture manifold decomposition is that we'll given a surface as inside M and gamma, we can have M prime, right? We can decompose the three manifold along the surface and have a new suture on it. Gamma prime on it. Okay, so right. So I cannot, well, let's see. Yeah, maybe let me explain the suture manifold decomposition by looking at an actual decomposition. Okay, so for example, well, this is our suture manifold. Well, it's very easy to verify this is a balanced suture manifold, and it's actually also taut. And we have the surface S, here the meridian disk, and we specify an orientation of the boundary of S to specify an orientation of the surface. And so, well, given the surface, we can decompose the suture manifold. Right, so the three manifold, well, is just obtained by decomposing the original three manifold where along the surface. And now we have the suture. Well, so this is the original suture, but right now the sutures are cut into arcs. So we want closed surface, we want closed curves to be suture. So we also have the orientation of the boundary of S, right? So S this. So at the end point of those arcs, so we just go along the orientation to put part of the boundary of S into the suture, right? So this is the original surface and the suture manifold M and gamma, and here is the new suture manifold. Of course, well, this is also due to Gabai. So, yeah, if you want to know more about suture manifold decompositions, then you can go to have a look at Gabai's original paper. So, right. So, why do we care about suture manifold decompositions? Well, that is very important because we can use suture manifold decompositions to decompose an arbitrary taut suture manifold into some very simple pieces. So this is the theorem by Gabai. Right, so suppose we have a taut balanced suture manifold. Well, of course, well, balanced suture manifold is only a subset of all taut suture manifold, but today, well, I'm going to focus on the case of balanced suture manifold. Okay, so if we have a Taut balance switcher manifold, then there is a finite sequence of decompositions. Okay, so we start from our M gamma, and we can find a surface S1 to get M1 gamma 1, and then, well, there will be a second surface M2 gamma 2, and we decompose. But it will end at a finite step, so that, well, each Mi gamma I is Taut, and Mn gamma n is a product switcher manifold. This means, well, there exists a surface with boundary F, so that Mn is just -1, 1 cross F, and the switcher gamma n is just a 0 cross the boundary of F. Okay, so this is a product switcher manifold. It's just a second surface. Okay, so yeah, so this notation is the one for a switcher manifold decomposition. So this notation means we decompose Mn gamma along the surface S1 to arrive at a new balanced switcher manifold M1 gamma 1. All right, so Gabai's theorem states that there is a finite sequence. Right, so this is very important. So we will end we'll end up with a product switcher manifold in finite step. And this leads to a very important definition about the depths. So the depths of a balanced switcher manifold is the minimal n in any switcher manifold hierarchy of this M and gamma. So right, so let me add this definition about hierarchy. Right, so well, this sequence, right, the sequence star is called a hierarchy of the original balanced switcher manifold. Right, so this is a sequence of decompositions make M gamma to be a product switcher manifold, and the depth is the minimal possible step for us to achieve this decomposition. Okay, so this is switcher manifold and decomposition. All right, so yeah, so Gabai's theorem tells us that, well, this decomposition is always finite step, or maybe the depth of a Taut switcher manifold is finite. But the basic question to ask is, well, can we bound so can we find some bound for this d of M and gamma? All right, and the theorem by Yuhash well, bounds the depths from the rank of the sutured Floer homology. So say if the second homology of M is 0, of course, well, M and gamma is Taut, then and we have an actual assumption that the rank of the sutured Floer homology of M and gamma is at most, well, is strictly smaller than 2 to the k plus 1's power, then the depth is at most 2k. Okay, so here SFH is the sutured Floer homology for balanced suture manifold. Right, so it's so you can consider it as an abelian group. It's a finite rank abelian group, and it's associated to any balanced suture manifold and serve as a topological invariance. Okay, so and well, this is, and the construction of suture Floer homology is using Higa-Floer theory, but there are many other Floer theories we can deal with. So in Instanton theory, this is the work of me and my collaborator, that, well, if we're having the same condition, but this time, well, we look at the dimension of the suture Instanton Floer homology, and that's strictly smaller than 2 to the k plus 1's power, then d of m gamma is at most 2k. Right, so here SHI is the sutured Instanton Floer homology. Right, so this is introduced by Kronheimer and Morovka. Right, so it's a finite dimensional vector space associated to any balanced suture manifold. It also serves as a invariance for balanced suture manifold. Okay, so we can bound the depths for Taut suture manifold. Okay, so right. So next, I'm going to talk about foliations. Right. So what is a foliation? Well, and we focus on codimension 1 foliation. In the 3 manifold. Right. So this is kind of, we're having a 3-dimensional space, but we slice it into surfaces. So locally, a foliation, so the leaves of a foliation looks like the horizontal plane. Right, the xy plane, and they are parametrized by the z coordinate. Right, so you can imagine at every local we just have this we just slice the 3 manifold into surfaces, and at every local the surfaces are the horizontal planes and parameterized by z-axis. Well, right, so a more intuitive example is about the codimension 1 foliation of a band, well, this band is a surface. So codimension 1 means, well, each slice is actually a curve. So you can imagine, well, there are infinitely many curves there, and each one of them is a leaf of the foliation. Okay, so yeah. And for foliations, well, there is a very important concept called Taut foliation. So let me make this definition. Of course, we look at codimension 1 Taut foliation. On a balanced suture manifold. Is called Taut if, well, we have a few conditions. Well, F is transverse to A of gamma, right? So when we say F is transverse to A of gamma, we mean every leaves of F is transverse. And now when we say tangent, that means every leaf of F, well, is tangent to, or just say some leaves of F is tangent to gamma, to R of gamma. And third, well, if we restrict our foliation, and this has no rib component, and well, last, well, each leaf of F intersect a transverse curve or arc, or properly embedded arc. Okay. All right. So yeah. So what is this rib component? Well, A of gamma is an annulus, and the rib component is something look like this. Right, and of course, well, this is well, this will rotate round and round. So so this will rotate infinitely many times. And well, yeah. So for more for more details about rib components, well, please maybe you can go back to Gabai's original paper. So this is called the Taut foliation. So the importance is that, well, Gabai shows that any Taut balanced suture manifold admit a Taut foliation. Right. So this is a very important theorem. Right. So I have no time to talk about the depths, and also about our main theorem. So I will leave them in the second part of the talk. Okay. Thanks.